There is a theory which states that if ever anyone discovers exactly what the universe is for and why it is here, it will instantly disappear and be replaced by something even more bizarre and inexplicable. There is another theory which states that this has already happened. Douglas Adams. So today we'll be discussing some common misconceptions about space, time, life, the universe, and everything. Some of these are pretty well known but have a twist. Some are well-known misconceptions but actually wrong themselves. And some are sadly less known, and we'll be correcting those today. We have a lot of topics to cover, from common misconceptions about space, that it is cold or dark or empty or quiet, to grander ideas like where the edge or center of the universe are, its beginning and end, and how we might travel around it, see new worlds around alien suns, and even survive the death of the stars themselves. I feel obliged to say from the outset that this episode is going to have a lot of actually moments, where it might seem like a nitpick, and a few probably really are. Tastes vary, and some are really there for completeness or bearing on more important misconceptions or less well-known ones, including how some of our worldview is constructed around these concepts and is arguably flawed or at risk of being blinded to new evidence or correct conclusions because of them. This episode is not about pointing out a few irrelevant technical errors that really have no relevance to day-to-day life and to poke at the realism of a given work of science fiction, though we'll do that too, but to suggest different ways of looking at the universe and our place in it, both now and in the future, and indeed many of these become relevant in the very deep future, eons from now. The YouTube version of this episode has been chapterized to make it easier for individual viewers to jump to specific topics of interest, but as always, our episodes are written and created with the principal intent of being watched as an episode, not a reference book. It's going to be a longer episode than most, so a drink and a snack might be advisable. I thought we'd start off by quickly hitting 5 big qualities of space that get assumed, one of which people get right but understandably can't really wrap their heads around, and 4 others that get misunderstood. Those 5 commonly misunderstood qualities which I've listed are that space is huge, that it has no gravity, that it is not dark, that it is not cold, and that it is not empty. Everybody gets that space is huge, but trying to really wrap your head around just how huge is just not doable. It is immense in a way that only numbers can describe, rather than experience, and even those of us used to math and scale have to constantly work to not make horribly off-target speculations simply because of how non-intuitive everything is. Earth is huge, but understand that if you're on a tall hill or skyscraper, being impressed by how much of it you can see, the whole landscape or cityscape around you is maybe one single letter in the entire big book of the planet's surface, and your whole lifetime and the lifetimes of everyone you know takes place during a period that's only a page in humanity's own history, itself barely a page in this planet's. There is no understanding of that immensity, and yet the tiny fly speck of your or my existence against the story of this world is still big compared to the minuscule dot that our world is in the crushing hugeness of this galaxy, which in turn is only trillions of the size of the known universe, which itself might be a speck against the great total of reality. There is no managing something like that in the mind, and as we'll talk about nearer the end, the shadow of that immensity sits very heavily on science and science fiction, influencing a lot of our perspectives, even while at the same time nobody ever really manages to truly capture the colossal nature of space and time. Some of the other aspects of space are not so hard to capture though. For instance, the confusion that space has no gravity is a big misconception. When orbiting an object, whether it's our space station around Earth or Earth around the Sun, the nature of the mechanics involved are basically placing you in freefall, perpetually. But just like when an elevator starts or stops, gravity isn't in any way shutting off. On the space station, you're only a few hundred kilometers up. The planet itself is thousands of kilometers wide. Gravity is only a few percent lower up there. It's just that you are orbiting by constantly being flung sideways as gravity pulls you down, and that is constantly changing the direction gravity is coming from, so when your speed is just right, and there's no air in the way, it allows you to essentially fall right back to the same spot over and over again. Air is critical here because orbit right over the Earth's surface and the air drags your speed down. We only put satellites as high as we do because that gets them above the air drag. We literally want them as low as we can possibly get them. See our episode on stratospheric satellites for more on that. Stop the space station though with a magic hand and you will fall right to the floor. Nor is it really zero gravity. There are lots of other forces and minor variations. It's just minimal, and so we call it microgravity. Normal gravity, what we have here on Earth, is 9.8 meters per second squared, or 32 feet per second squared, and what we call 1g, much as we call Earth's distance from the Sun 1 AU or astronomical unit. The Sun and Moon's gravitational pull on Earth are what causes our tides, moving trillions of tons of water and ground along. If we froze Earth in place and removed it, so just the Sun was pulling on us, it is just under 1,000th of a g, and on the Sun's surface it is 28g, and the escape velocity from the solar system from Earth's position is 42 kilometers per second, almost 4 times what the escape velocity from Earth's surface is. It's more than 10 times that to escape to the galactic rim. There is no known natural place where you can't feel gravity or escape its effect, and even stuck in the center of a planet or between 2 identical and massive objects, like a pair of binary neutron stars or black holes, that merely means the pull of gravity is balancing out. The time dilation experience there remains enormous. As gravity slows the passage of time, the stronger it is in total, not net. Much like gravity, there is no place free of light in space either. Space is not dark, and only in the shadow of a planet or moon is our sun ever not shining all day every day, and it is actually brighter than here on the ground, even at high noon, and perpetually so. Even out on distant Pluto, during the daytime, you would have light comparable to modest room lighting and much brighter than the full moon. Out in deep interstellar space, there's an ambient starlight that varies in intensity and spectrum, locally a bit over 1% of the full moon, which means you could see enough to walk around, if clumsily without a flashlight, even on some dead frozen rock in the Oort cloud. Alternatively, inside star clusters or the galactic bulge, it might be hard to find any place that wasn't at least full moon bright all the time, and many places where darkness is only inside buildings or caves. The average color of starlight in the observable universe is a shade of yellowish-white beige named cosmic latte, though for a time, from miscalculation, we thought it was more of a turquoise. Either way, there's always light. There is also tons of radiation in other frequencies, from radio and microwave up to X-ray and gamma. Most of the universe is indeed darker than daytime or full moon light, but the notion that space is pitch black is wrong. The darkest places are always those in shadow. Similarly, the notion that space is cold is also wrong, though that needs several qualifiers. First, cold is not really a science term, as some measurement but more of a relative state. Something is hotter or colder than something else it's compared to. What we have is temperature and total heat, or thermal energy in something. The air in a hot oven is much hotter than a pot of boiling water, but that water contains a lot more mass than the air in that oven has, and any given material also has a thermal capacity. Air has only about 1/6 of the thermal capacity of water, so raising the temperature of a kilogram of water by a degree takes 6 times the thermal energy a kilogram of air does. There is also thermal conductivity, which is how quickly something leaks or absorbs heat. Styrofoam is low and slow to change, while metals are quick, which is why you can keep your coffee warm in a styrofoam cup in the winter and not burn your hand touching it, while touching metal can give you quick frostbite or burns in the summer, even though they're roughly the same temperature as everything else there. Space is not empty, but it is nearly so we don't really lose or gain heat by conducting it out of ourselves there, or by convection, merely by radiation. This is why stars burn so hot. They are actually very thin and cloud-like by and large, especially the large ones. Our sun is only slightly denser than water overall, only about a quarter the density Earth is, and its upper regions that we actually see are even thinner than air, nothing like the implication we often have of it being a big ball of fiery lava, and more on that later. But the sun doesn't really end there. What we call the surface is just a photosphere, the place where most of its light comes from. It's not the hottest place or the end of the sun, and there's no real definition for the end, it just gets much thinner. Most of the matter in our solar system is far hotter than the hottest places on Earth, and even our own core is not terribly hot. Gases have their temperature basically off of how fast they are moving and what they are in terms of atoms and molecules, and so a place with fast-moving gas might be so thin in density that you only had a few atoms per cubic meter, and thus less heat energy than an ultra-cold cube of ice has, and yet its temperature might be 1,000,000 degrees. You could still freeze to death in it, as you radiate heat faster than you absorb sunlight or starlight, or for that matter cook to death, just depends where you are. If we exposed you to the vacuum, then you would freeze only in the sense the liquid state of matter, as opposed to solids and gases, which only exist where there is pressure, and the range of temperatures they exist at narrows as pressure lowers, and widens as it gets higher. Water freezes at 0 Celsius and boils at 100 Celsius at normal pressure, but boils at much higher temperatures under greater pressure. You actually get a mixture of both the boiling and freezing of the water that is in a human that is suddenly exposed to space. So it's not really wrong to say someone freezes in space, especially as if they're decently far from a star. The remaining water will stay that way rather than boiling off, which is why water ice is ultra common in the outer solar system but not the inner, and is why comets have those beautiful tails. It is actually kind of weird because we also tell people that the universe is cooling over time as it expands, and this is true if we're talking about the average temperature of a given cubic meter of empty space, as opposed to the average temperature of a given atom in the universe. However, the actual average temperature of deep space is much higher, about 2 million Kelvin, versus more like 200,000 10 billion years ago. This might seem at odds with saying the universe is only about 2.7 Kelvin, way colder than Antarctica or even Pluto, but that's the temperature of the cosmic microwave background radiation, or CMB, permeating everything and thus is the coldest you can get anything down to currently. Like a big hunk of metal floating in deep space that rapidly radiated off its own heat, but was so big and dense that the occasional collision of a couple atoms, even if they are millions of degrees, just doesn't do anything to warm it. Nor is the CMB the only type of ambient radiation out there, just a very old one that's basically everywhere. Which takes us to the misconception that space is empty, as there's something like 500 million of those CMB photons left over from the dawn of the universe passing through any cubic meter of space at any given time, even in ultra-deep space out in the cosmic voids between galactic filaments and walls. Ignoring dark energy for the moment, there is plenty of other random matter even out in those voids, indeed even whole galaxies, but inside galaxies the density of space is a lot higher. It is ridiculously tiny compared to here on Earth, the densest known body in the solar system, curiously, but it is not empty, and we have regions of space where the interstellar dust and gas is a lot higher than in our solar system at large, millions of times so, and it is much denser than the intergalactic void. Even beyond that though, if we block off every form of radiation getting into some shielded volume and find and pull out every single atom floating around, we still have the reality that we normally think of as reality, but is actually built on a quantum universe. Everything going up here is a statistical byproduct of quantum mechanics at that scale, and down there everything is in a constant state of uncertainty, with packets of energy and matter popping into existence and right back out again, after lengths of time so tiny that they make a second look like untold eons. But just as billions of photons of light can zip through a volume of space every second, each there for less than a billionth of a second, as long as the light source is still emitting photons in that direction and at the same rate, that volume of space being measured will still have a constant density of new migrant photons. Like traffic on a road, nobody lives there, but it's always busy. So too, all these particles flickering in and out of existence for fractions of an instant do cause a net density, and this is everywhere all of the time, so even a sealed off vacuum, space is never really empty, and indeed when we add in dark matter, which would casually pass through any shield more easily than a neutrino, and dark energy, which seems to just add tiny packets of new space, which contains energy, everywhere all the time, space can never be said to be empty. That won't stop you from asphyxiating in space though, as empty is pretty relative. But when it comes to the notion of exploding when you get pushed out an airlock into a vacuum, that is no more real than rapidly turning into a brittle ice statue that would shatter moments later if bumped. Explosive decompression was really popular in science fiction, and I'm glad to say has mostly been retired as a trope, Pressure differences can be brutal, but the force just isn't there to tear you apart. It is a difference of just 1 atmosphere, and you can experience the reverse by swimming down about 10 meters or 32 feet underwater. Go about 3 or 4 times deeper and get about 3 or 4 more atmospheres of pressure. Normally, space is basically 0 pressure and Earth air is about 1 atmosphere of pressure, so that difference isn't that much. Nobody is getting sucked through a bullet-sized hole in the wall. Maybe one that was almost as big as them would have enough pressure to squish them through, but otherwise they just plug the hole. Nor does all the air rush out in moments. Poke a little hole in a spacesuit or a space station wall, and air will leak, but rather slowly, and you can just put your finger over it or tape it. The water in your plumbing is often under several atmospheres of pressure, and yet a hole in a pipe can be covered and doesn't rip things open. You could put your finger over it with fair effectiveness. If you're wondering what a hole in a spaceship would be like to handle, grab a vacuum and turn it on and put your hand over the wand, or a bike pump and put your finger on the nozzle and press the pump handle about halfway down, compressing air to about 2 atmospheres of pressure. If you're thinking that a household vacuum isn't a total vacuum, it's probably also fair to point out that most space missions are at partial pressure too, keeping the oxygen content of air high but going low on nitrogen to slow leakage. Leakage occurs at the rate of pressure difference, half your pressure, half your leakage rate. There is no noise in space. In space, all is silence, and everyone knows that, and it's mostly right. Sci-fi movies often ignore it to add in sound effects, and you can get some stirring battle scenes as they switch perspectives from the loud battle setting to one of total, terrifying silence, as explosions dot the eternal dark void. And again, this one is mostly right, but needs caveats. First, sound is vibration, and you will get it wherever there is a medium of matter to travel through. So anything hitting or landing on your ship or station still causes bangs and clunks. If you're running around a voided ship or asteroid mine touching the ground, you're going to feel vibrations through it and thus noise. Plus, there's no real place that is a total vacuum, so there's never really an absence of sound. There are plenty of places in the universe where the interstellar medium is a lot thicker than local space, and indeed you can hear sound very high up in our own atmosphere long after it would be unbreathable. We actually have heard a black hole that was in a galactic cluster with so much gas that it vibrated, and we can read that vibration electromagnetically and play it. It is decidedly eerie. Black holes suck. Speaking of black holes, the notion they suck everything in and destroy all matter nearby is another case of not exactly wrong, but yet very wrong, as naturally occurring black holes might be several kilometers across and absolutely fatal to touch or get fairly close to, but they are basically harmless compared to the supergiants that form them, millions of times brighter than our own sun, and many millions of kilometers wide. They are safer to be near than a planet even, as you are only in danger from them from the radiation they emit from slowly sucking in gas, or if you are so close that tidal forces will rip you asunder, and both of those would be vastly closer to that black hole than you could normally be near even a dim small star. They are stealthy to be sure, but you would detect the potentially lethal radiation long before it got dangerous to you. So the idea that a black hole is going to sneak up on your ship as it travels, even if for some reason you had no map to warn you, is just wrong. So is the idea that you cannot escape a black hole. You don't really fall into black holes any more than you do stars or planets, and indeed less so since only the most highly elliptical orbits would crash into a black hole event horizon. The entire reason they are surrounded by radiation is because getting into a black hole is nigh impossible. Particles of gas and dust fall toward it and generally miss, unless they are almost perfectly on target, and then fly away, and some enter an orbital pattern. They spin around that star and have gained huge kinetic energy from the fall, and ram into each other. This causes a slow formation of an accretion disk and bits of matter occasionally falling in, and is really no different than a planetary ring except higher energy. Your spaceship is either going to bend its trajectory a bit when passing that black hole, or simply enter an orbit of that black hole, probably a highly elliptical one, and most likely the former, as we tend to assume interstellar vessels are moving around 10% of light speed, if not much more. and even a 10 solar mass black hole only has an escape velocity of 7% of light speed at a distance equal to the radius of our entire planet Earth, which is more than 20 times its own radius of 30 kilometers or 20 miles, which is just absurdly tiny in space terms. Moreover, it's important to understand what actually happens as a ship hits a gravity well, which is to say, it falls and speeds up. This doesn't make it harder to get out. It's just like rolling down a hill, then rolling up another. You have all that extra speed helping you on the climb, plus no air drag slowing you down, though the accretion disk could serve that role of brake too. Also, you can then boost with your thrusters a bit to get out of that orbit, just like if you were moving around a planet. This is how slingshot maneuvers and the Oberth effect work, letting a ship gain speed moving around a massive object. If you dally too long though, you will get slowed down by passing gas and dust, and get beat up on by high energy radiation, which can also slow you, and then you might fall in or be ripped to bits, but you might also use that local matter and radiation to power your way out of that black hole, and they might be a good place to refuel at or set up interstellar space station hubs like truck stops. See our episode Colonizing Black Holes for more discussion of that. And if living and walking near a black hole bugs you, remember that you are living even closer to a big ball of molten radioactive matter with a thin crust floating on it that we live on. Black holes may end up as the interstellar traveler's best friend, allowing course corrections and gravitational slingshots that could never be done around another body at interstellar speeds and without crashing into them or burning up. Don't get too close though, they are only mostly harmless. If you fall across the event horizon of a black hole, you are stuck in there, even if you survive the trip, as this is specifically the distance at which light speed equals the escape velocity of the black hole, though that event horizon moves relative to you, and you'll never actually reach it as you fall. If you had some way to move faster than light speed, you might get out, though it should be noted that many FTL concepts, like the warp drive, would still be stuck in there, as their cheat method of crunching and expanding spacetime fore and aft is ineffective against the black hole's own gravitational warping of spacetime. Nothing goes faster than light speed. The notion that nothing in the universe can go faster than light is uncomfortably at odds with the issue that most of the galaxies we can see are now moving away from us faster than light speed, and yet there is no contradiction. What we really mean is that if you're trying to jog along and keep up with a photon of light, you're going to lose, or at best keep up with it if you're another massless particle. However, space expands, and we assume bits and pieces of new spacetime are constantly emerging randomly everywhere, probably as tiny subatomic bits at the Planck scale. If you imagine a very long measuring tape where people are quickly splicing in new bits of tape between its endpoints, then the rate those folks work and how many of them there are is going to control how fast that tape expands, and as it expands, more people can fit in there splicing even more tape. It will grow, and once it is long enough, those folks will be expanding that tape faster than a sound wave could carry the voices of any of those people down the line to the guys on the end who now have to run away faster than sound. This just scales up in space to light speed, and the galaxies on the other end of our measuring tape aren't doing any pulling. They aren't moving locally at any high speed, but they are moving away from us faster than light, and we only see them now because the light from them reaching us left back when they were closer and moving away slower. That rate is roughly 7% of light speed for every billion light years between you and the object currently. Double or half that distance, double or half that expansion rate. And again, nothing is moving in the universe faster than light speed. It's just over far enough distances that expansion is so fast that nothing moving at light speed could cover all the new space emerging between it and its destination as quick as that space is forming. The edge of the universe is 13 billion light years away. This means that the effective edge of the universe is 13 billion light years away, since things expanding away from us at light speed would presumably have been doing so since the universe formed 13 billion years ago. And everything about that statement is wrong. First, the current estimate for the age of the universe is 13.8 billion years, rounding comfortably to 14, but for a while the estimate was closer to 13, and that number got rather stuck in common discussion. We should say 14. When I was a kid back in the 1980s, the estimates were generally 7 to 20 billion years old, and you would see 20 in a lot of the texts of the time, and that narrowed to 9 to 14 billion years in the 1990s. That was calculated off Hubble shift, and we were finding stars that might be much older than 9 billion years by then too. You have probably heard of stars estimated to be older than our universe, but almost all of that comes from having stars with plus or minus a couple billion years on their age having their upper margin fall over those same wide margin of the potential universe ages. Stars formed before the first billion years of the universe had passed, so if your estimate is saying the universe is 13 to 14 billion years old, and you've got a star calculated as 12 to 14 billion years old, there is no real implication you have a pre-universe star there. However, if light from such a star, one made just after the universe formed and 13 billion years ago, were to be detected today, it would mean that it was 13 billion years old, and that's usually how astronomers would describe it. The photon doesn't have any sort of clock on it, of course, but the longer and further it has traveled, the more redshifted it is, and we can make pretty good guesses off it and its companions as to what wavelength it started off at, to see how much it redshifted and thus get that age. It does not mean it left that star from 13 billion light years away though, or that's that far away now. That photon covered that much distance, but most of that distance did not exist when it started towards us, and most of it emerged behind it afterward, in terms of discussing how far a star or galaxy is from us now at this moment. And if we wanted to send a reply or a ship to that star or galaxy, it would be even further away and moving even faster away. Back when it left, that star was probably less than 1 billion light years from where we were then, not that Earth existed at that time, and now if we could just freeze everything, it would be around 45 billion light years away, and that return message would take 45 billion years to reach that, again if we froze universal expansion. But since we cannot, at least with current technology, if we try to send a signal to that spot, it would never reach it, as it is currently traveling away from us at somewhere around 7 times the speed of light. The universe has no edge. What we usually call the edge of the universe is the CMB, or cosmic microwave background radiation. This is because the further back or out you look, the more redshifted everything is, till it gets kind of dark, because there were no stars or galaxies yet. Then we get to a period that's fairly high infrared because the universe was still a pretty dense and warm place, and if you go back a little further, you get a place where it's dense and warm enough to resemble the light from stars, just a very hot plasma mostly made of hydrogen. It was even denser and brighter before that, but we can't see there because light emitted from then constantly scattered and absorbed rather than traveling very far before hitting something. There was a critical point where things expanded and cooled enough that hydrogen shifted to a less absorptive state, and things were just spread out more and less likely to scatter, and this was about 380,000 years after the Big Bang. This surface of last scatter is as far as we can see with anything electromagnetic, and thus it gets dubbed the edge of the universe a lot, and 380,000 years is very tiny compared to several billion, so it's close enough to the Big Bang. But if we ever got better at detecting neutrinos, we could probably look all the way back to the first minutes after the Big Bang. And this edge is only in a temporal sense. We have no idea where or if the universe has an edge, only that we could never reach it without a faster-than-light spaceship, assuming space is not infinite. Some folks would say that there's no space beyond that edge. That might be the case, but there's no evidence for that. It is one of those examples where folks are speculating and extrapolating off mathematical models and logic, not data, and that's not really science anymore. It is entirely possible the Big Bang is merely a local event in a wider universe, or that the universe Big Banged but was already infinite when it did so. We examine this more in our episodes on the Big Rip and the edge of the universe. The universe has no center. One of the governing principles of modern physics since Isaac Newton's day was that the universe has no meaningful center and that we certainly are not the center itself. That is 100% at odds with the observable data, incidentally. As we discussed a moment ago, we can see equally far back and out in every direction till we hit a wall of cosmic microwave background radiation, that surface of last scatter. This is literally a spherical shell around our planet that is expanding constantly out from us, showing ever more redshifted photons from ever more slightly further away. We are not the center of the universe. Since we can see equally in all directions back to the surface of last scatter, the default interpretation of that is that Earth is the center of the universe. That is what the science says. We choose, from habit and logical extrapolation, to assume that the universe keeps going a long way beyond that, and that either it is infinite, in which case a center arguably does not mean much, or if it is a big sphere, it is one in which we probably are of no place of specific note, and there may be places in the wider universe where folks cannot see beyond a certain distance in one direction. Or it may be that things curve back on themselves, like the surface of a sphere such as Earth, or maybe the universe is the surface of an expanding 4D sphere, though probably not. Or donut, or like walking out the edge of an old video game and popping back in on the other side. Key thing, we do not actually know, but we got in the habit of assuming ourselves no place special back in Newton and Copernicus's day, and that was very cosmologically and philosophically important to them at the time. Humanity and Earth are merely mediocre and not special examples of anything, and that's essentially the default opinion of science. And perhaps ironically, it is an opinion that is not scientific itself. It is merely a speculation, albeit a very sound one based on logic, but not physical data. It is fairly important though to be mindful of blinders because we discussed the Fermi paradox a lot on this show, and the default view from the available evidence is that there are no detectable alien civilizations, and that they probably do not exist anywhere near us, even on the galactic scale. This is essentially the entire paradox, because if we are not special and we are not the center of the universe, it should be absurd to approach contemplating the universe from that perspective. It is probably no better an idea to assume Earth and humanity are tiny mundane dots on the cosmological scale, a pale blue dot, as to assume we are the shining center of creation. But more importantly, we have a historic scientific basis for saying humanity is not central, that is improperly conflating our physical location with our metaphysical importance, and it is rather baked into our thinking. It might be right, too, but let's poke at that notion a bit. Earth orbits the Sun. To shift back home to Earth, we can continue that notion of us not being the center of the universe by pointing out that Earth does not actually orbit the Sun, nor does the Moon orbit Earth, and nor is the Sun in any way the center of our galaxy. Orbits occur based on all the mass in play in an area, and in our solar system 99.8% of that is in the Sun. 0.1% is Jupiter, and the other 0.1% is everything else, but mostly Saturn. How in play stuff is at any moment is based on its distance too. It can be seen as a quibble, but if we're contemplating life on other worlds, and how our early understanding of the heliocentric model and Copernican mediocrity principle altered our worldview and philosophy of science, we need to be mindful that other places aren't going to see it that way. Life that evolved on a planet around a close binary star system is in a good position to spot that. Those stars seem to orbit something themselves that they cannot see, and one can speculate how that might be impacting their early philosophy and religions. For all near-term purposes, we really need to finish getting away from the notion that Earth and all the other planets circle the center of our Sun, rather than orbit elliptically, as it results in a confused view of things. Of course, being aware that Earth orbits elliptically can cause confusion too, as folks often think Earth is close to the Sun in summer. In truth, the seasons have virtually nothing to do with how close or far Earth is from the Sun at any given moment, and perihelion, when we're closest to the Sun, takes place in early January, and early July, the height of summer, at least for the Northern Hemisphere, is our aphelion, our furthest distance from the Sun. Earth's orbit is fairly circular as these things go, and we define its normal distance from the Sun as 1 astronomical unit, or AU, but it gets as close as 0.983 AU at perihelion and 1.017 AU at aphelion. That's 3.5% further out than when closest, which also gets 7% more sunlight than when furthest. This is hardly trivial, it's just dwarfed by the effect of axial tilt. Other planets with greater eccentricities, which is most of them, would likely have a weather and seasonal cycle strongly affected by that eccentricity, and even tidally locked planets around dimmer red stars can have significant seasons as a result of that eccentricity, and made all the more weird by them potentially having orbital years a few months or even weeks or days long. Speaking of red dwarfs though, we often hear our sun called a fiery yellow dwarf, and that is really wrong in every respect. To our eyes it definitely has that golden shade, but all stars are white light sources with a peak wavelength of radiation, and our sun's peak is a bluish green. Alternatively, most of the photons coming off it are actually in the infrared. Indeed, most stars emit the majority of their light in the infrared range of the spectrum we can't see, as did the typical incandescent light bulb, and even the dimmest and coolest red dwarf is still as white a light as those old bulbs were. This isn't surprising, as most stars are red dwarfs, though again they don't look red at all, and the entire cataloging process is basically a flawed one of it being much easier to see big, bright stars. The Copernican or mediocrity principle failed us there. We saw the abnormal giants most, brighter than our own sun, not the normal stars, most of which are tiny and dim compared to our own. A star's visibility over distance is based off its brightness, diminishing with the inverse square of that distance, so one that's 100 times brighter is visible 10 times further away. However, space is three-dimensional, so that same volume of space contains 10 cubed or 1,000 times as many stars, meaning that our early observation of the universe contained virtually nothing but giants, and very few stars even as dim as our sun, which is bigger than 95% of all stars and 10,000 times brighter than the dimmest red dwarf, yet there are stars a million times brighter than our own sun. Needless to say, the sun is not in any way on fire either. While oxygen is the third most common substance on the sun, there are no molecules. Everything is glowing hot plasma, cooling itself off by radiating waste heat as sunlight, and fusion occurs deep below in the core, and very slowly too. Your typical ton of solar core matter emits about enough power to run a light bulb. It's just that there is so much of it, and will keep doing so for billions of years before dying, and our sun is short-lived compared to most. It will live only 10 billion-ish years, and the overwhelming majority of stars that ever formed thus far in our universe are still alive and kicking. Of the 500 billion or so stars in this galaxy, perhaps 10 billion have become white dwarfs, just a couple percent, and only a tenth of that, perhaps a billion total, have gone supernova and become neutron stars, and only about a tenth of that became black holes. Of course, our sun will die someday, and this is part of why we talk about wanting to travel to the stars and colonizing other worlds, and this takes us to our penultimate misconception for today, that time on spaceships runs much, much slower. Now, this isn't wrong, but there is a tendency when we see discussion of spaceships that do not have FTL for us to say they are moving nearly light speed, but the reality is that in a no FTL universe, you are not likely to be plowing through space at 99.9% of light speed. The energy needed for that, even ignoring practical engineering in the rocket equation, is literally 2,000 times what it would take to move at 10% of light speed. And at 10% of light speed, your clock is only moving 0.5% slower than normal, or about 7 minutes a day or 6 months a century, and at 1% light speed, it's only 4 seconds a day that you're saving, 26 minutes a year. That is not really letting you sneak away from the Grim Reaper by slowly crawling forward in time. And even at 99.9% of light speed, your clock is only moving 20 times slower than normal. You don't even get down to half normal time flow till 87% of light speed. Faster is always better if you've got the energy and ability to do it, When it comes to trying to escape local time, instead of using more energy than the entire modern planetary economy uses in a whole year to accelerate one person to a high time dilation rate, why not use that same energy to power that economy and all its research labs and crack the secret of freezing and restoring people from cryo, or maybe even some advanced type of stasis field? In the end, even though our sun is one of the shorter-lived ones, and stars will keep forming and living for many trillions of years to come, they do eventually stop forming naturally, and that takes us to our final misconception, that the universe ends when those last stars do. And this is a dual misconception because it would seem very unlikely any natural stars will even form in our galaxy a billion years from now, simply because a vast galactic civilization isn't likely to let them form. Artificial fusion, energy by dumping matter down black holes, or by the slow evaporation of black holes, or even by vacuum energy, are all plausibly on the table as superior ways to keep the lights on for your stellar empire than by actual starlight, and that doesn't even contemplate higher Clark-Tech options, which they would have had billions of years to research before the cosmological event horizon sweeps away all the stars from sight that you have not colonized. Indeed, as we saw in our Civilizations at the End of Time series, that time after all the stars are born out and all is swallowed in darkness might be a far brighter, longer, and more populated era of civilization than all of those which came before combined. There are still so many things we don't know about the universe, and likely many other misconceptions we have about it, but hopefully one of those will turn out to be that in the end all must run down and die from entropy, and that it will turn out that the clock can be wound back, or that the sum total of reality is far bigger than even the seemingly endless enormity of our universe. So it's the end of another school year, and for a lot of folks it's a time of transition in life. We're just not sure where that's supposed to be. I didn't find my niche till I was in my 30s, and these days there really is no one-size-fits-all approach to pursuing or creating your dream job. To find your niche, and to take advantage of the opportunities when they come up, you'll need to explore and acquire skills. For me, when it came to making this channel a reality, not just an occasional amateur hobby, that involved having to learn everything from graphic design to marketing, how to edit audio, how to film on camera, how to do animations, improving my writing, and many more. It was very daunting, but it was, and is, doable, especially with a good partner like Skillshare and their community of learners. Skillshare is a great resource for quality videos on those topics and many more, but one that I'd particularly recommend is Danielle Crissa's Creative Breakthrough, 8 exercises to power your creativity, confidence, and career. This channel has a lot of very smart and creative people on it, where coming up with a good idea isn't the problem. It's that road mapping to developing into a success that is, and believing that you can actually do it. Starting with her Power of Aha moments, her videos on Skillshare help explore how to move from that basic idea into something more formed and practical, along with how to manage your creative talent to keep your confidence high, banish blocks, and silence self-doubts. Maybe you want to start a business or write a novel or develop a game or become a YouTuber or a podcaster. Maybe you just want to learn to paint or take a better photo. No goal is too small. Skillshare can even help you find more time for your goals by helping you with productivity and time management, for which I'd highly recommend the videos there by my friend, Thomas Frank. Take control of your future and make it a reality, and let Skillshare help you. Try them out today by using the link in this episode's description. The first 1,000 people to use the link will get a 1-month free trial of Skillshare. So normally we have our live stream Q&A the last weekend of every month, but I will be down in Frisco, Texas that weekend to help host the International Space Development Conference. So the plan is to have the live stream next weekend, Sunday, May 21st, but I'm also going in for some minor surgery on my nose and tongue earlier that week. So we might need to cancel, and I'll probably sound a bit different, hopefully in a good way, as that's rather the point. It is supposed to be the next step in fixing my speech impediment, but the live stream is the tail end of the main recovery time for the surgery, so I might not know till the last minute if I'm good to do the show. Speaking of the show, this weekend is our Sci-Fi Sunday episode on May 14th, where we'll explore the grim realities of super-urbanized hive worlds. Then we'll have its companion episode, Hungry Aliens, on May 18th. And in 2 weeks, on May 25th, we'll talk about how to bend space and warp reality. Then we'll head into June to look at exploring and settling the Kuiper Belt. If you'd like to get alerts when those and other episodes come out, make sure to hit the like, subscribe, and notification buttons. You can also help support the show on Patreon, and if you want to donate and help in other ways, you can see those options by visiting our website, isaacarthur.net. You can also catch all of SFIA's episodes early and ad-free on our streaming service Nebula, along with hours of bonus content at go.nebula.tv/isaacarthur. As always, thanks for watching and have a great week.